Let's look at the chain rule in a case where we have multiple independent variables. In the past examples, we've seen cases where we have multiple intermediate variables, but we are going to focus on multiple independent variables. Let's examine the function w, where w comes from, the dependent variable w, where w comes from the function f, which takes in g, h, and k. But notice that g, h, and k, these are functions of r and s. So r and s are the real independent variables. When we make our diagram, we'll start with r and s, the independent variables at the bottom. We're going to send those to the intermediate variables, which I've chosen to call x, y, and z. So if we take r and s and plug them into g, we get x. If we take r and s, we plug them into h, we get y. If we take r and s, plug them into k, we get z. If we group together x, y, and z, plug them into the function f, we get w. Now, looking at this diagram, we can see that we might ask a question like, how does w change with respect to one of the independent variables? We can only pick one. So we can ask a question like, how does w change with respect to r? Or we can ask a question like, how does w change with respect to s? But since there isn't a single unified independent variable, we're going to use partial derivative notations for either one of these choices. W depends on multiple variables. So when we write these derivatives, we want to remember to use that partial derivative notation to make sure to communicate that this is an incomplete picture. W with respect to R is not the full picture. W with respect to S is not the full picture. Now, I almost always get a question of, what if I added them together? Would I be able to use the regular D here? Well, let me ask you this. If you could, what would you write? dw, d what? The only way to do this would be if you could find one variable that both independent variables depend on, and then we could do a chain rule there. But that's not the case here. We do not know that r and s are related at all. Based on the way that this function's written, my guess is r and s are completely independent of each other, so we can't do one total derivative. We can only do two separate partial derivatives. Now that we've clarified that, let's take a look at each one of these partials. If we wanted to ask the question about how w changes with respect to r, we should isolate that portion of the diagram. So looking at our full diagram, if we're just asking about r, we're going to keep only r in the bottom for the independent variables. We're going to leave s aside. The intermediate variables are all copied over, same with the dependent variable. Now when we read our diagram, we can see that w is going to x, so we'll have partial w with respect to x, and then x is going to r. But remember, x came from that g of rs function. So x depends on both r and s. When we take the derivative of x with respect to r, that's a partial. So we're going to do partial w with respect to x times partial x with respect to r for our first term. These are both partial derivatives. Next, we can move down the middle branch. So we know w goes to y, and then y goes to r. So from w to y, that would look like partial w with respect to y. And then from y to r, because y is a function called h, a function of r and s, we know that this would be a partial as well. Partial y with respect to y, partial y with respect to r. And we have one more branch to go down. W goes to Z, and then Z goes to R. Again, remember that Z is that function K, which takes in R and S, which means when we take the derivative of Z with respect to R, that's also a partial derivative. So our last term is going to look like partial W, partial Z, times partial Z, partial R. When we add up all of these terms together, we get the partial derivative of W with respect to R. We can do the same thing, but for the partial with respect to S. And I'm not going to walk through this entire diagram, but I encourage you to. See if you can come up with the notation for the partial derivative of W with respect to S, and then match it with what I have written at the top of the screen on the left, right here. So see if you can create that diagram, read down all the branches, and see if you get the same thing that we have here on the screen. All right, let's go ahead and practice using these. We're looking at a question that asks us to find two partial derivatives. The first one is asking for the partial of Z with respect to U. The second one is asking for the partial of Z with respect to V. Looking at the equations that were given, we can see that Z is our dependent variable, X and Y are the intermediate, U and V are the independent. So for each one of these partial derivatives that we're calculating, we'll draw a separate diagram. Let's start first with the partial Z with respect to U. In this case, the only independent variable we're looking at is U. We know that U goes to both X and Y. X and Y are grouped together and sent into another function to create Z. So to make our to make our chain rule equation, we're going to read down partial Z with respect to X, partial X with respect to U. And then we're also going to read down the opposite side of the branch, which is partial Z with respect to Y, partial Y with respect to U. We'll calculate those terms, add them together, and that will give us the equation for partial Z with respect to U. So let's go ahead and calculate those. We need to calculate four partial derivatives. We need Z with respect to X. We also need Z with respect to Y. We need X with respect to U. We also need Y with respect to U. Looking at our definition for Z, 3x squared minus 2xy plus y squared, taking the derivative with respect to x would come out to be 6x minus 2y. And doing the partial with respect to y would leave us with minus 2x plus 2y. Moving down to find the partial of x with respect to u, we look at 3u plus 2v. The partial with respect to u would just be 3. Moving on to the definition for y, we see 4u minus v. The partial with respect to u would just be 4. We're going to take all four of these pieces and plug them into our expression for partial z with respect to u. We have 6x minus 2y times 3 plus negative 2x plus 2y times 4. And we do want to replace x and y with their function of u and v, because we don't want x, y, u, and v in our expression. We are asked to write this in terms of u and v only. So we need to pull out the x's and y's, replace them with the functions of u and v. Before we do that though, I want to simplify this as much as possible. That way we're only plugging x into a few number of places rather than at least 2 places like we have here. So we'll distribute this out. We'll get 18x minus 6y minus 8x plus 8y. We can combine our terms here to get 10x plus 2y, and now we will replace x and y. So we know that x is 3u plus 2v. We know y is 4u minus v. So when we go to write our, oh, I don't want to write it all the way up there. When we go to write our final expression, dz du, we have that 10x plus 2y, but we're going to replace x and y with their definitions. So that'll look like 10 times 3u plus 2v plus 2 times 4u minus v. And we can clean that up a little bit. 30u plus 20v plus 8u minus 2v. Even cleaner, 38u plus 18v. So the partial of z with respect to u, in terms of u and v, comes down to this really simple expression. Now let's do the second half of this problem, which is finding the partial of z with respect to v. Similar diagram. We will have v as our only independent variable. We know v goes to x, v also goes to y. X and y group together to create z. Using our chain rule, which I'm just going to write out up here at the top, the partial of z with respect to v, that involves partial z with respect to x times partial x with respect to v, plus partial z with respect to y times partial y with respect to v. We need to calculate all of these partials. Notice that we did already calculate 2 of them. So the partial z with respect to x, partial z with respect to y, we have those already done for us, which is awesome. The only extra thing we need is the partial x with respect to v, partial y with respect to v. So partial x with respect to v, that's just 2. Partial y with respect to v, that's -1. Let's go ahead and plug in the partial z with respect to x, partial z with respect to y, and then we can clean this up. So we've got 12x minus 4y. I have a -1 times a -2x, so we get 2x. A -1 times a positive 2y, we get -2y. Take that even further, we get 14x minus 6y, and now we will replace x and y. So we get 14 times 3u plus 2v minus 6 times 4u minus v. Multiply that out. And once we multiply that out, simplify, we find that the partial of z with respect to v is 18u plus 34v. I had to kind of rush through that last 3 lines because I'm only able to record 15 minutes at a time right now. So these are examples of how to use the chain rule in the case where we have multiple independent variables. Try a couple. Let me know if you have any questions.